TTL Computer 2. Today, we're going to begin our implementation of TTL Computer 2 using our digital simulation software. And the name of that software is Digital, and it's written by H. Neiman. And you can search for this on the internet and make your way to the project page. And you could download a copy of this for yourself and play around with the software and start your own simulations as well. Okay, I'm going to close this down and we're going to get going. Okay, so I mentioned in our introduction that we were going to start out looking at the clock circuit for the computer. And I said this really kind of is the heart of the computer. And right, this really controls the timing and synchronization of everything that occurs on the computer. And one of my unstated goals for the project is that I really want to have a solid, stable, and reliable computer. None of those glitches that we dealt with in my TTL computer. And to do that, the real key thing is that we need to have clearly defined states and state transitions. Okay, so let's just jump into this. And what I'm going to do now is the real cool thing about digital is this. I'm going to hit the play button. And that really starts our simulation. And this circuit is now live. And so I'll take the approach over the next few videos of just pointing out different features and elements of the digital simulation software rather than doing a full introduction. We'll just do it as we go along. Okay, so a couple of things to note about digital. We see some of these lines are light green, and that indicates an active high signal is on those lines. And some are dark green, and that's an inactive low signal on those lines. Also, we have these squares. These indicate inputs in the circuit, and we have the circles rather, that indicate outputs for the circuit. So we have a few inputs for the clock. We have the run signal, which puts the clock in run or not run mode, which puts the whole computer in run or not run mode. We have a clock signal in, and there's this is just a component. It'll be included in a larger design, and that design will have the real clock signal that feeds the clock circuit. So that's what that is here. And the other is the clear signal to clear the clock back to reset the clock, and that's a negative active. Okay, so let's set this up to run. We want to put this in run mode, and we want to we want the clear signal inactive so that the counter can run. And now we see up here that we have a kind of an oscilloscope, and we'll get that going in a minute. And what we've implemented here is basically called as a ring counter. And we have two dual D flip-flop circuits here, and each output feeds the input to the next D flip-flop. And then the last output from the last flip-flop is fed back to the input of the first. And that gives us kind of a shift register that loops back to itself and produces a circle. And I'm going to just clock the signal now, and we can see that. You see the one signal here is high, the next signal is high, and so on through the four output signals. So our output signals from the circuit is the N clock signal, the P clock, the U clock, and the T clock. And we see those up here in the oscilloscope. We can see that how those work. And we can see that basically these signals follow each other, right? Each signal precedes the prior signal. And the P clock I call either the process or the pulse clock. The U clock is the update clock, The T clock is the counter's clock, and the N clock is the negative clock. And if we think back to the Ben Eater computer, that clock signal in his implementation only had two states. It had a positive clock and a negative clock cycle, and that's all that it had. So the negative clock cycle here does correspond, to the Ben Eater negative clock cycle. But what I've implemented here is I've broken down the positive clock cycle into three separate signals, right? The P clock, the U clock, and the T clock. If we combine those together, right, they would make up the positive clock signal in the Ben Eater implementation, and then again the negative clock cycle. So that's how that works. So we can see how those signals operate. And so you can ask yourself, Charlie, why did you do that? And how are these signals going to be used? And I said, one of the significant things to have a reliable computer is we need to have clearly defined states and state transitions. So let's take a look at, all right, so each of the elements or components in the computer are going to use different clock signals to change state. And I have a little diagram here, which I'm going to make this larger now so it's easier for you to see. Okay, so again, we have the P clock, the update clock, the T clock, and the negative clock. So the P clock signal is going to control loading of the X, the instruction register, the flags, and the RAM and the devices are all going to change states or be clocked in on the P clock cycle. On the U clock or the update cycle, the A, the B, the C, and the stack pointer will be updated on the U clock cycle. And that's basically, these are all the registers that can be destinations from output from the ALU, right? So those will be loaded in the U clock cycle. And then the T clock cycle is for updating the memory address register and the program counter. Okay, so I have some example microcode steps below here that we're going to walk through that'll help kind of illustrate how these signals are used. Okay, so we'll take a look first at this first microcode step, and this is actually the last step in our fetch cycle, right? So we have RAM out, we have the instruction register in, and then we increment both the program counter and the memory address register. Okay, so let's walk through this. So we start out in the negative clock cycle, and the controller raises all these signals in the negative clock cycle. Now we proceed to the P clock, and we see that the instruction register is updated on the P clock, on the B clock cycle. So next, the instruction register would be loaded. Then we hit the U clock cycle. None of these registers are used in this microcode step, so nothing would happen in the U clock cycle. And then we hit the T clock cycle, and we can see that both the program counter and the memory address register are updated in the T clock cycle. And then we go back to the N clock cycle. So we can see how the elements that make up this step were executed in a specific order based on the P clock, the U clock, and the T clock. Now, in the Ben Eater computer, all of these would have just been executed as one event, all at the same time. And with this solution, we're doing this, we're executing this step in a very definite order and sequence to have the updates occur. And again, that's key. That's key for reliability in our system. And then our next example, in this example, we're adding the A register and the X register. We're doing the add, we are updating the flags register and then updating the results back to the A register. So again, we start out in the negative clock cycle, and the controller raises all of these signals. We hit the P clock, and we see that the flags are updated by the P clock. So the A and the X are out on the bus. The ALU does the add, and then the P clock cycle updates the flags. We go to the U clock cycle, and we see again these registers are clocked on the U clock. So we have the A register would be clocked in, and then the T clock. None of these registers are in play in this instruction, so nothing happens. And then we go to the negative clock cycle. So again, the purpose of these additional clocks is to execute the individual elements of the microcode in a very defined order. And again, the key reason why we're doing that is to have very clearly defined states and state transitions. Right? Again, if we do this all in one tick, in my view, we're open to having race conditions on what's going on between the different components, and introduces the possibility of glitches or ending up in an invalid state in the computer, and we don't want that to happen. Okay, so that's kind of a walkthrough on the different clock signals that come out of the counter. And one other thing that we have a little extra logic down here, and for the run signal. So if I'm going to get to all right. So we just started the P clock cycle up here. So now let's say we wanted to pause the computer or stop the computer. So we're lowering the run signal. Now I'm going to still clock the counter, and we're going to see that the counter is going to continue. Right? We see there that's the U clock has still been raised, the T clock has been raised, and now we're in the negative clock, and now the computer is halted. So we have this little extra circuit here just so that when we go to the not running state, that we always end up with only the negative clock in the negative clock cycle, which really is it's the T0 state. It's the beginning clock for the next instruction. So we always want to end up again in a known and a valid state. We wouldn't want to pause the computer like mid-execution on a microcode step. We always want to complete a microcode step to get to that known state. And then the clock could, resume again. Okay. All right. So I think that's everything we wanted to look at today. A little bit of a lot to take in with all of these different the different clock elements and how we use those. We're going to use those in the system, and then so we'll see as we proceed through the implementation that some elements of the computer will change state based on the P clock, some on the U clock, some on the T clock, and even some on the negative clock. And we'll see that again in our implementation. Okay, so I think next week, our next video, we will take a look at the instruction set as I've kind of have it defined so far, and that's still fluid, I think, but we'll look at that in our next video. So that's it for today. Thanks for watching.